In the Shiomi Bay area of Tokyo, Koto Ward's Shimizu Corporation, a major Japanese construction company, has built a new research facility called Novare. The name Novare comes from Latin, meaning to innovate or renew, symbolizing its commitment to pioneering new technologies and nurturing talent for future innovation in construction. The facility integrates cutting-edge technologies, such as producing formwork for walls with 3D printers and adopting robots to reduce labor needs, making it an excellent testing ground for next-generation techniques. The Novare Innovation Hub is exploring how the future of construction should evolve toward the new era. The Japanese construction industry today faces serious challenges, one of which is a chronic labor shortage. The 5.84 million construction workers in 2004 had dropped to 4.83 million by 2023, a plunge of over 1 million over 2 decades. The aging workforce is another significant concern. The proportion of workers over 55 years old rose from 28% in 2004 to over 36% in 2023, and those under 29 years old represent only 12%, a drastic decline in younger workers. Starting in April 2024, new regulations will increase limits on overtime, further exacerbating the labor shortage. Additionally, the rising prices of construction materials, such as concrete, steel, and timber, have caused costs to rise significantly, making the industry environment extremely challenging.
The concept of innovation is being actively discussed in various sectors today. We must consider what value we can create for our customers through our work. To achieve this, we need to foster talent with new ideas, methods, and under unprecedented conditions. Looking ahead to the next 10, 20, or even 50 to 100 years, we needed to establish a facility that focuses on nurturing people for the future. And this is how this project began.
In October 2020, a groundbreaking ceremony was held to pray for safety. The construction of Novare began amidst the COVID-19 pandemic. Many different methods and skills are needed to build something on this scale. Typically, when making walls or pillars, wooden panels hold the shape of the walls as concrete is poured in around rebar. Once the concrete hardens, the panels are removed and the wall is complete. It is one of the basic fundamentals of construction. If not sturdy, it can shift or create gaps when the heavy concrete is poured in. Therefore, formwork must be performed by highly skilled workers. A great number of panels are needed for large-scale building projects. While relying on highly skilled workers had been the norm, Shimizu Corporation automated formwork panel fabrication using Building Information Modeling, or BIM. A 3D BIM model of the building plans are made on a computer, including important information about materials such as lengths, widths, and types. The data from the BIM models were used to automatically generate the required formwork plans. Specialized software drafts formwork construction blueprints, automatically converted from the BIM data. These blueprints are then used to program the automated processing machines to fabricate the formwork panels.
Formwork consists of temporary structures used in building construction and doesn't typically rely on formal blueprints. Traditionally, they have been built based on the knowledge and experience of carpenters and skilled craftsmen. However, as the number of these craftsmen continues to decrease, high-quality formwork like theirs may not be produced consistently, and we needed to ensure efficiency. Using BIM construction blueprint data, we can generate processing plans, allowing machines to use that same data to produce formwork that matches the data precisely. Our focus is on enhancing efficiency through these automated processes.
3D printers are being incorporated to create formwork panels and further improve efficiency. This wall column has complex curves, measuring 20 meters in width and 4.5 meters in height. It was made using one of Japan's largest 3D printers, developed by Shimizu Corporation. Unlike traditional wooden panels, this technology allows not only straight lines, but also intricate curves to be built freely. The printer moves along a rail, and the formwork material is accurately layered at 10 centimeters per second. Once the formwork is complete, concrete is poured directly into it. The formwork does not need to be removed afterwards and remains as the exterior wall.
Using the unique advantage of 3D printing, which is to create free-form shapes, this design reflects the optimal structural form. The shear force was a critical factor in determining how thick the wall should be. Areas experiencing the highest shear forces are made thicker, while those with lower shear forces are kept thinner. This also allows for a reduction in the amount of concrete used compared to traditional rectangular formwork, which lowers CO2 emissions, making it more environmentally friendly.
The shortage of skilled labor remains a pressing issue. Utilizing robots is one solution to this problem. This is a newly developed welding robot. Here, two robots are welding symmetrically and efficiently on a steel column. The robot arms are equipped with laser sensors that detect the shape of the welding area. An AI calculates the procedure, and the robots carry out the welding. They can execute tricky angled welds with the precision and skill normally required of numerous highly experienced workers.
With the declining number of professionals with lots of experience, I think that a robot that anyone can operate is probably a pretty good solution.
In order to protect buildings from fires, a new type of robot to spray fireproof material on walls has also been adopted. The robot can operate automatically according to parameters such as the shape and height of steel beams and the areas to be coated. These robots significantly reduce the burden on workers.
The fact is, workers must wear weatherproof jackets, masks, and goggles, even in hot weather, which makes the job quite physically demanding. It's our main goal to lighten the burden on the workers by letting machines perform some of these tasks.
Traditional Japanese techniques are also being utilized. This ceiling features a hybrid roof structure made of wooden beams and steel frames. The wooden beams are arranged to support the steel roof from below, greatly decreasing the amount of steel needed. They have a complex shape with curved tops to prevent deformation from concentrated pressure at the center. This design provides solid support for the building while maximizing the aesthetic warmth of wood. Using traditional Japanese methods, these beams create very strong joints without the need for nails or metal fasteners. One is the awase kanawa joint, and the other is the kaiten kanawa joint. These techniques have been used in Japan's wooden construction for centuries. Shimizu Kisuke, the founder of Shimizu Corporation, began his career as a carpenter in 1804. These techniques continue to be passed down over 220 years later. Following the Kumamoto earthquake in 2016, the firm restored the Romon Gate of Aso Shrine, an important cultural property, as well as reconstructing Okinawa's Shurijo Castle, which was destroyed by a fire in 2019. During the Novare project, robots were used to process the wood for the ceiling. This is a wood carving robot. It utilizes 3D models of joint data to intricately carve even the finest curves.
Because the process involves repetitive machining, it was very helpful to identify any issues early on and apply those lessons to subsequent processes. After repeated machining, we were able to achieve increasingly cleaner finishes toward the end.
A vast number of steel frames and wooden beams are needed for wood-steel hybrid roof structures. A new method has been introduced for installation procedures as well. It's normally necessary to either set up scaffolding at every work location or move it around as the work progresses. In this case, a method that allowed workers to stay in place by sliding the roof itself was used, also helping to shorten the construction period. Temporary platforms were set up in one part of the building where the wood-steel hybrid roof was assembled, divided into 3 units. Once a section was completed, it was slid into position along the eaves using hydraulic jacks. Reducing the amount of temporary scaffolding needed significantly decreased the effort of setting up and moving it. The construction, which took about 3 years starting from October 2020, involved around 350 partner companies and approximately 240,000 people in total. Nagata Masamichi, the construction manager overseeing the project, stated that while technology is important, it is communication between people that is essential.
Welding
With the development of robo-welder, wood-carving robots, robo-spray, the diversification of robots has been very beneficial. At the same time, it's crucial to value human emotions. The connections between people are important, even when they come from different professions, have different clients, or work on different designs. If we can't unite those feelings, we won't be able to build great buildings. In the future, I hope we can embrace digitalization and automation with robots, making it easier to create buildings that are still rich in human touch and emotion.
A stately wooden residence stands on the facility grounds, surrounded by the newer buildings. This is the former Shibusawa residence, former home of Shibusawa Eiichi, built by Shimizu Corporation in 1878. Shibusawa is a prominent figure in Japan's history, featured on the new 10,000 yen banknote and often referred to as the father of modern Japanese economics. He was a leading entrepreneur who founded the First National Bank and served as its president. The construction of his home was entrusted to Shimizu Kisuke, the second-generation head of Shimizu Corporation. Impressed by Kisuke's skills, Shibusawa commissioned him to build his residence, a two-story Japanese wooden house completed in 1878. As part of Novare's development, this historic building was relocated and rebuilt on-site. Deconstruction began in February 2019 with careful manual disassembly. Each of the over 20,000 components was numbered and documented to ensure accurate reassembly. During the reconstruction, which began in 2020, traditional techniques were employed. Instead of completely replacing deteriorated or damaged sections, only smaller parts were swapped out. Techniques such as grafting and reinforcing with steel plates were used to preserve as much of the original materials as possible.
The legacy of the continuous challenges that our predecessors faced is reflected in this building. As for this time, we also faced various new challenges as well. I believe the value of the former Shibusawa residence is in its ability to incorporate the trends and technologies of each era, while leaving a lasting legacy for future generations.
The building is a valuable example of architecture, skillfully blending traditional Japanese and Western styles. In 2024, it was designated as a tangible cultural property of Koto Ward, Tokyo, under the name of the former Shibusawa residence. Novare is conducting experiments and technological development for the future. This large-scale experimental space is equipped with some of Japan's top-class testing capabilities. Advanced research and development in architecture, building materials, and robotics are being conducted in collaboration with other companies. A key piece of equipment is a machine capable of applying one of the largest pressure loads in the country, 30 meganewtons, equivalent to the pressure at the very bottom of an over 400-meter tall skyscraper. It is vital for testing the durability of components used in the foundations of these buildings.
In recent years, both domestically and internationally, the number of high-rise projects has been increasing. For these projects, there's a growing demand to verify performance under conditions as close to reality as possible. That's why we have introduced facilities capable of conducting large-scale load tests like this.
The open, glass-walled chemical analysis lab is researching how to produce concrete with lower carbon emissions, addressing the significant carbon dioxide output normally associated with it. Various environmentally friendly construction materials are being developed here. A key feature of this area is its open concept design. The office area is located in the center, and employees can directly observe the experiments and tests taking place around them.
By organizing the office area in this way, we hope to encourage interactions among researchers from different fields, as well as foster connections with universities and manufacturers from various industries. This collaboration is intended to spark new innovations.
Initiatives exploring new possibilities in the construction industry through collaboration with other fields are also being explored. This is the purview of the Corporate Venture Capital, or CVC program, launched in 2020. Through this program, Shimizu Corporation invests in startup companies with innovative technologies and develops joint projects with them.
We're shifting our perspective on construction from being a goal to viewing it as a means. This approach allows us to engage not only in the construction industry, but also to explore various other fields.
The aim is to combine expertise and know-how in architectural construction techniques and civil engineering with the cutting-edge technologies and business models of startup companies in order to create new value. As an example, the CVC program is collaborating with technology startup Light Blue to develop a vehicle-mounted AI surveillance camera system called Kawasemi. This system can automatically detect people and vehicles in blind spots behind heavy machinery using AI, issuing a warning when necessary. The AI analyzes images to identify human skeletal movements, determining what tasks are being performed. If the person is detected to be unaware of the machinery's movements, the system can instantly detect and issue alerts through sounds, lights, and monitor displays.
Collaborating with Shimizu Corporation is significant for us because they are a leader in the construction industry and are engaging in research and development that may not lead directly to immediate profits. It not only expands our business network and opportunities, but also helps us gain valuable insights into their industry expertise and the needs of construction sites.
The facility is also being utilized to develop future talent. The construction industry is often referred to as experience engineering, as many skills can't be learned without hands-on experience. To facilitate this, full-scale models and mock-ups allow students to see and interact with real-life examples up close, helping them adapt to the field more quickly. In the civil engineering area, there are mock-ups that replicate railway viaduct construction and underground work, the underlying networks that make everyday life possible. In the architecture area, there are displays of buildings made from reinforced concrete, as well as precast concrete components assembled in factories, providing opportunities to learn about many common construction methods.
It's very easy to imagine how the work on these structures will progress in the field, which I enjoyed very much.
I was able to learn things that I haven't yet experienced in my actual work, making my time here very valuable.
These learning areas utilize the latest digital technologies. Through the use of AR and VR, participants can engage in digital simulations for tasks like rebar inspections and how to visually check for construction defects.
With all the significant advances we've made, We wanted to give back to society by offering resources to university students. We hope to inspire young people who are considering a career in the construction industry and encourage more of them to enter the field. We also want to engage high school students and, if possible, even younger grades.
The Green Transformation Initiative aims for decarbonization and is being put into practice here. Rooftops fully equipped with solar panels are now a common sight, but it doesn't stop there. This facility utilizes excess solar energy to electrolyze water and produce hydrogen. It's stored in a hydrogen storage alloy, allowing it to be extracted as needed for power generation through a system called hydrocubic. This newly developed alloy can absorb hydrogen up to 1,000 times its own volume, making large-scale storage possible. Storing hydrogen directly in tanks requires large containers and poses explosion risks if ignited. However, the hydrogen storage alloy eliminates ignition risks, making it safe for indoor installation in buildings. Additionally, test demonstrations have shown that the alloy can be rapidly filled with green hydrogen produced off-site to power the building. This safe and reliable power system allows each building to function as its own environmentally friendly hydrogen power station.
There are many challenges in society that can't be solved by the construction industry alone, but I believe there are also many issues that we, as people knowledgeable about construction, can address. Therefore, by leveraging the support of those around us, we can work together to find solutions. We truly believe that would be a wonderful thing to achieve.
The various initiatives aimed at fostering innovation and developing future talent at Novare represent the firm's relentless dedication to taking on challenges, even after over 220 years since its founding. This program was made possible by Shimizu Corporation.